Hello guys, and welcome to my YouTube channel. In this video I am going to explain the I2C communication protocol, focusing on addressing, acknowledge signals, and clock operation. I2C is a synchronous serial communication protocol that normally uses only two signal lines. SDA carries the serial data, while SCL carries the clock signal. One controller, commonly called the master, communicates with one or more peripheral devices on the same bus. Both SDA and SCL use open drain outputs. This means devices can pull the lines low, but they do not actively drive them high. Pull-up resistors connected to the supply voltage return the lines to the high state. Every peripheral has an address, allowing the controller to select one specific device. This makes I2C useful for connecting sensors, EEPROM memories, real-time clocks, displays, and many other low-speed peripherals while using only two microcontroller pins. The I2C bus consists of two shared signals, SDA and SCL. SDA stands for serial data and carries address bits, data bytes, and acknowledge information. SCL stands for serial clock and synchronizes every transferred bit. Both lines normally remain high when the bus is idle. This happens because SDA and SCL are connected to the supply voltage through pull-up resistors. A typical starting value is 4.7 kilo ohms, although the correct value depends on bus capacitance, supply voltage, communication speed, and the current sinking capability of the connected devices. I2C devices use open drain outputs. A device creates a logic low by switching its output transistor on and pulling the bus toward ground. To create a logic high, the device releases the line and allows the pull-up resistor to raise the voltage. Because every device follows this rule, multiple devices can safely share the same SDA and SCL wires without directly driving opposite logic levels. Each I2C peripheral is identified by an address. The most common format uses a 7-bit device address, followed by one read or write bit. The address bits are transmitted from the most significant bit to the least significant bit. After the 7-bit address, the controller sends the direction bit. A 0 indicates a write operation, while a 1 indicates a read operation. For example, a temperature sensor may use address 0x48, a real-time clock may use 0x68, and an OLED display may use 0x3C. All three devices can share the same SDA and SCL lines, because only the device matching the transmitted address responds. After receiving a valid address, the selected peripheral normally generates an ACK signal. The other peripherals ignore the rest of the transaction. Remember that the address written in a datasheet is usually the 7-bit address. Some software libraries require it to be shifted left by 1 bit before transmission. An I2C transaction begins with a start condition. During normal data transfer, SDA must remain stable, while SCL is high. Therefore, a start condition is identified when SDA changes from high to low, while SCL remains high. After start, the controller transmits the 7-bit peripheral address and the read or write bit. These 8 bits are followed by a 9th clock pulse used for the ACK or NACK response. If the peripheral acknowledges the address, one or more data bytes can be transferred. Every data byte contains 8 bits and is transmitted most significant bit first. Each byte is also followed by an acknowledge clock. The transaction ends with a stop condition. Stop occurs when SDA changes from low to high while SCL remains high. The complete basic sequence is therefore start, address, ACK, data, ACK, and stop. More advanced transactions may use a repeated start, instead of releasing the bus with a stop condition. In I2C, every transmitted byte is followed by a 9th clock pulse used for acknowledgement. During the first 8 clocks, the transmitter controls SDA and sends the address or data byte. Before the 9th clock, the transmitter releases SDA. The receiver then controls the acknowledge bit. For an ACK, the receiver pulls SDA low during the 9th clock pulse. This indicates that the address or data byte was accepted successfully. For a NACK, the receiver leaves SDA released, so the pull-up resistor keeps the line high. A NACK after the address may mean that no device uses that address, the peripheral is not powered, the wiring is incorrect, or the device is temporarily busy. During a read transaction, the controller becomes the receiver. It sends ACK after each received byte when more data is required. After receiving the final byte, the controller sends NACK and then generates stop to end the transaction. The I2C controller normally generates the SCL clock and controls the communication rate. One clock pulse transfers one data bit. During standard data transfer, SDA should only change while SCL is low. When SCL is high, the data must remain stable so that the receiver can sample it correctly. Start and stop conditions are special exceptions because SDA changes while SCL is high. Common I2C operating speeds include standard mode at up to 100 kHz, fast mode at up to 400 kHz, and fast mode plus at up to 1 MHz. Every device on the bus must support the selected speed. Some peripherals use clock stretching when they need additional processing time. The peripheral holds SCL low even after the controller releases it. The controller must wait until SCL actually becomes high before continuing. Clock stretching support depends on the microcontroller hardware and driver, so it should always be verified when selecting devices and configuring timeouts. This example writes the value 0x80 into register 0x01 of a peripheral using the 7-bit I2. See address 0x48. The controller first generates start and sends the device address with the right bit set to 0. When the peripheral recognizes its address, it pulls SDA low during the 9th clock and generates an ACK. Next, the controller sends the register address 0x01. The peripheral acknowledges this byte. The controller then sends the data value 0x80 and waits for another ACK before generating stop. In STM32 HAL, the 7-bit address is commonly shifted left by 1 bit when passed to the transmit function. The 2-byte transmit buffer contains the register address first and the data second. The function then sends both bytes in one transaction. In a real application, always check the returned HAL status so that address NACKs, bus timeouts, and communication errors can be detected instead of being ignored. Reading a register normally begins with a short write phase. The controller first generates start, sends the device address with the right bit, and then transmits the register address that it wants to read. Instead of ending the transaction with stop, the controller generates a repeated start. It sends the same device address again, but this time with the read bit set to 1. The peripheral acknowledges and begins transmitting the requested data. The controller generates ACK after every received byte when additional bytes are required. After the final byte, the controller sends NACK and then generates stop. A repeated start keeps control of the bus and prevents another controller from interrupting the combined transaction. For STM32 applications, functions such as HAL, _I2, C_mem_read, or the sequential transmit and receive APAs are normally more appropriate when a true repeated start is required. Two independent blocking transmit and receive calls may insert a stop between operations, depending on the driver implementation. One major advantage of I2C is that many peripherals can share the same two signal lines. In this example, the controller is connected to a temperature sensor at address 0x48, a real-time clock at 0x68, and an OLED display at 0x3C. All devices are connected in parallel to SDA and SCL. The controller selects a device by transmitting its address at the beginning of the transaction. Only the matching peripheral responds with ACK and participates in the data exchange. The remaining devices monitor the bus but ignore the transaction. Each address must be unique. If two devices use the same fixed address, they may respond simultaneously and create corrupted communication. Some components provide address selection pins that allow one or more address bits to be changed. Only one effective pair of pull-up resistors is required for the bus. Multiple modules may already include pull-ups, so their combined resistance should be checked carefully. When I2C communication fails, begin by checking the physical bus. First, confirm that the controller and peripheral share a common ground and use compatible voltage levels. Check that both SDA and SCL have pull-up resistors and remain high when the bus is idle. Next, verify the 7-bit device address. Confusion between 7-bit and shifted 8-bit address formats is one of the most common causes of an address NACK. An I2C scanner can help identify which addresses actually respond. Using a logic analyzer, confirm that a valid start appears, followed by the expected address, read or write bit, and ACK. If SDA or SCL remains permanently low, disconnect devices one at a time to locate the device holding the bus. A stuck peripheral may sometimes be recovered by releasing SDA, toggling SCL up to 9 times, generating a stop condition, and reinitializing the I2C controller. Also check for clock stretching and configure a reasonable timeout instead of assuming every low clock period is a fault. Thanks for watching this video, guys. Please share, like and comment below. Also subscribe to my YouTube channel for more videos.